Hi class, in this video we're going to move into section 10.4 and talk about areas and lengths in polar coordinates. So the first thing we want to do is talk about areas in polar coordinates. So let me talk about this picture here. In this section we're going to look at areas enclosed by polar curves. Okay, note as well that we said enclosed by instead of under, as we would typically have in other problems. These problems work a little differently in polar coordinates. So like here's a sketch of an area that we might be finding in this section. So here is the distance r, or the first part of the polar coordinate, and it's some function of theta. And then our angle here for polar coordinates is going to go from theta is equal to alpha to theta is equal to beta. So we want to find this green shaded area here. All right, so we're going to be looking for this shaded area, and the formula that we're actually just going to use to find this is going to be the integral from alpha to beta of 1/2 times r squared d theta. So it's really just a straight application of the formula. So it's slightly different from the fundamental theorem of calculus in this case, but just following this formula, you'll be able to find it actually pretty easily. So we can expand on this if you have two curves. So to determine areas that are enclosed by a single curve, but what about situations like the following sketch here where you want to find the area between two curves, so between this first red one and this blue one, this green area here. In this case we use that same formula from the previous slide to find the area enclosed by both, and then the actual area is just the difference of the two. So really it's just the area is equal to the integral from alpha to beta of 1/2 the outer r value minus the inner r value, each of these squared with respect to theta. So it's a just straight application of this formula. Okay, so let's do one example so you can see how this works. So let's find the area enclosed by one loop of the four-leafed rows given by r is equal to cosine of 2 theta. So we want to find this little blue rose leaf right here. Okay, so notice that in this figure that the region enclosed by the right loop is swept out by a ray that rotates from theta is equal to negative pi over 4 here to pi over 4 here. Okay, so what this is telling us here is from here to here, this is telling us the lower bound of integration to the upper bound of integration. And this is telling me the r right here. So if you look back at our formula here, we've got 1/2. We know what r is. We know the starting angle. We know the ending angle, alpha and beta. So we can just plug it right into this formula and find that area. So area, again, we're going to integrate from negative pi over 4 to pi over 4, 1/2 r squared d theta. Well, I'm just going to pull the 1/2 out. Looking back, where does this come from, this cosine squared 2 theta? Well, that comes from the r right here, cosine of 2 theta. So the formula tells us to square it. So from here, what we're going to do, you'll notice why does this go from 0 to pi over 4 here and the 1/2 goes away? Well, looking back, really what we can do is we can just say the angle from 0 to pi over 4, and it's 2 of that area. Well, 2 times 1/2 goes away, so that's how we're able to simplify it to this. Now to be able to find this integral, you're going to have to power reduce this cosine squared 2 theta here. And when you do, you get the following. Once you've power reduced this, it becomes a piece of cake to integrate. 1 integrates to theta with respect to theta. Cosine of 4 theta integrates to 1/4 sine of 4 theta. Just plugging in our bounds of integration here, you can do this yourself. The final answer will end up being pi over 8. So really just this problem here just involves using the formula. And this one is a little bit easy and kind of straightforward to do.